Welcome to this lesson on exponents and reviewing the different things that we did in this course on exponents. Okay, I'm going to assume that most people do understand some basics about exponents, but just a little quick review here that when we take a number and we say x to the power 4, for example, that means x times x times x times x 4 times because that's what the power 4 represents. Okay, and I got to assume you do understand that basic thing. Now we talked about 4 different laws associated with, or 5 different laws associated with the exponents. And the first one was the product law, which states that if the base is the same, a being the base here, that the exponents will be added if we multiply two exponents of the same base. So examples include a to the power 4 times a to the power 3. This would be a to the power 7. And over here, a to the power 2, or sorry, 6 to the power 2 times 6 to the power 3 would be 6 to the power 5. Now this you could actually get a numeric value if you wish, and if you put this in your calculator, and you should know how to do this, you would get 7776. These can be very large numbers because that means 6 times 6 times 6 times 6 times 6 times 6. I believe I said that 5 times. So 6 times itself 5 times, it gets to be pretty big, 7776. And you do need to know how to use your calculator properly in order to do that calculation. And there is a special button on the calculator that usually has, mine it's like y to the power x, sometimes it's x to the power y. And you need to know how to use that particular function on your calculator. All right. The second law was the quotient law. And the quotient law says if the base is the same, in this case a is the base again, then the exponents, when they're divided, are subtracted. So x minus y. So in this particular case, a to the 7 minus 2 is a to the power 5. And then in this particular case, using 8 to the power 7 and 8 to the power 3, oops, that should have been divide. Let me just change that for a second and I'll make sure it is changed on yours. It doesn't make sense for us to oh shoot, of course, here we go. Just give me a second here. Go divide. There we go. Okay. And that would give us an answer of 8 to the power 4, okay, which of course we can put into our calculator if we want and get a number. So 8, and then I push the button that has the, in my case, the y to the x, and then it puts a little hat symbol and 4, and it gives me an answer of 4,096. Okay. And then we came to what's called the power law. And the power law is where the exponent to a power exponent. In this particular case, now we multiply the two numbers. So it has to be, a to the x to the power y, and then we just do a to the x times y. So the best way to look at it is through some examples. So a to the power 3 to the power 5 is going to be a to the power 3 times 5, which is 15. And over here, we use the numbers to do the same thing. So 9 to the power 3 to the power 6 works out to be 9 to the power 18. Not 9 to the power 9, because it's not adding, we multiply those two numbers, okay? I'm not even going to put that in my calculator to try to get an answer because it's going to be ridiculously huge, okay? And then we have the negative exponent law, and this is how we deal with negative exponents to make them positive, because basically they become 1 over and the negative sign disappears. So a to the negative x becomes 1 over a to the positive x. So this here becomes 1 over a to the power 6. And the same thing can hold true here, where we're using 4 to the minus 2 equals 1 over 4 squared, which actually equals 1 over 16. And that's exactly what it equals, is 1/16, okay? And then, of course, the last rule, which is the exponent of 0. So anything to the power 0 actually equals 1. And we did get into the explanation of how, if we use the quotient law, or we use the power law, product law, any of these laws, we can kind of come up with a system where we get one thing over the other that are equal to each other. And we know that 5 over 5 is 1. And so x to the power 5 divided by x to the power 5 should be 1 as well. But when we subtract, we get a power of 0. So this makes sense. So in both cases, the answer here is just simply 1. Okay. Now, I thought I'd throw one little example in just because, students always kind of get stuck on these things as we go. So here's an example that you might see on a test where you're asked to combine a number of these different things. And so let's look at each one separately. This is the power of a power law. So this is 9 to the power 18 divided by 9 to the power 15. And this is going to be all over, well, 0 times 3 is 9 to the power 0. So we end up with 1 on the bottom. So that's going to just disappear. That's just going to become 1. And dividing by 1 doesn't do anything because 9 to the power 0 is 1. And then here we have a division. So that's going to become 9 to the power 3 because we're going to subtract those two values, right? And 9 to the power 3 I have on my calculator, and I can find the answer to be 729. Okay, pretty straightforward. Okay, then we looked at roots. Mostly square root stuff is what we're going to do. There will be nothing on radicals, mixed radicals. That's actually really covered more in grade 10. I did cover a little bit of it, but not too much. So the square root of 49, most of you know how to do that. Again, it's a function of your calculator. You have a square root symbol on your calculator. And so the answer here is 7. But you really should remember that it can be plus or minus 7, right? Minus 7 times minus 7 equals 49, just as positive 7 times itself does. And we don't tend to see that always written. We tend to just see the answer 7 there. But as you know, moving forward, that may come into a play when we start solving equations and doing some other things, okay? Over here, we have the square root of a squared simply equals a. And then we always have these really funky ones here where the square root of something in brackets, well, that just simply equals x minus 3. And that's just, how it works, because x minus 3 times x minus 3 is what x squared means. And when we take the square root, we eliminate the square of the part that is in the brackets. And then, of course, you can have things like the square root of not perfect squares. So square root of 42, you need to use your calculator for something like this. You can't just memorize them, although we do memorize most of the perfect squares, right? And I will list those for a quick second, at least up to 12 times 12. This works out to 6.4807 ... Just keeps going on and on. It's what they call a non-repeating, non-terminating. Okay, usually round it off to a couple decimal places. I put 4 in there, but that's a little more than necessary. Now, with respect to square roots, there are some numbers you should try to become familiar with. It's really useful to kind of put this in your memory bank. The perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and it just keeps going. And if you're wondering where I'm coming up with these numbers, it's really straightforward. It's 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, and just keep going. And these numbers are worth having in your mental handbag, knowing them, recognizing them. They're special numbers when it comes to taking square roots and stuff like that. And once again, I will not have anything on the exam or culminating activity with respect to mixed radicals and entire radicals, so we can save ourselves there. Then we came to Pythagorean's theorem, which really is key, something you really have to keep in mind, and I think most kids know this, it's only for right triangles, okay? So it does not apply to triangles that are not right triangles, so we have to wonder if they are. And one of the things they love to do is ask you, is this a right triangle or is it not? And so you need to recognize, well, if it is, it looks to me like this is the angle that would be the right angle. So you go A, B, C, and then you say A squared, the left side equals A squared plus B squared, and that equals 3 squared plus 5 squared, which equals 9 plus 25, okay? And 9 plus 25 is 34, right? So we write the answer here as 34. And then we go to the right side, which equals c squared. And I'm getting this by the formula here. I'm assuming most kids have seen this before. C squared equals 7 squared, which equals 49. Therefore, these do not equal each other, and therefore this is not a right triangle. And if they equaled each other, then we know that they are correct. Okay, so I threw it on just as an example. This is not a right triangle. Okay, and then you could have one that is. So those kind of questions do show up from time to time. Then we have solve for a missing side, and so in this particular case, you'd have to know that this is a right triangle. So I should have had the right triangle symbol in there, and the answer we're looking for here is probably what we would refer to A, B, C. I tend to give A the smallest side, B the next, and then C, of course, always the hypotenuse here. And so A squared equals C squared minus B squared in this particular case. So A squared equals 13 squared minus 12 squared. And I believe that works out to A squared equals 25. If you work it out, this is 169, subtract 144. And generally speaking, I encourage kids to put this in their calculator. So you should be able to just go 13 squared minus 12 squared and say equals, and you get the answer 25. Now I need to square root both sides, so A equals 5, and when I do that, I square root both sides of the equation, okay? And therefore, A equals 5, and I should include my units, meters. It's not a word problem, so a therefore statement, I'm not asking you something in words like I was in the previous question where I said, is this a right triangle or is it not? Then I have to use a therefore statement. When it says solve for A, the missing side, then you don't have to do that. All right, and we moved on to something called scientific notation, if you recall. So I'll just scroll down. Scientific notation is just a way to express really big and really small numbers, okay? And we see this mostly in scientific principles. So what we do is we're going to move the decimal place always after the first significant digit. So what we're going to do is go 5.78, and then we're going to say times 10, and the number of times we move the decimal place is what the number 10 is. So I count here and I say, well, if I'm moving it from here to here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I think 14 times. And it's positive because this is a really big number, and for big numbers it's positive, and for little tiny numbers like the one below we say negative. So just again, and sometimes I'll just go 3, 6, 9, 12, and then 1, 2 more, that's 14 as a double check. And then here it's a similar process, except for we're going to move the decimal place way over to the far right, making the number bigger. So we're going to use a negative number. So it's 2.84 times 10, and then it's going to be 3, 6, 7, 8. Well, it looks like a weird number. 1, 2, 3, 4. Oh, I think I screwed this up. I'm going to change this a little bit here, just so yours will be changed. I'll change it before I send it out. I think the intention was to do it like that, so somehow they got screwed up. So 3, 6, 9, 12, and then one more would be 13. Okay, so that would be minus 13. Okay, and I often put in, spaces every third number. That's the new metric norm to do. Most of the world uses that methodology. Okay. Now the next one here is 3.72 times 10 to the 8th, and we want to write this as a regular notation, just to show you can put it in regular notation. And so this is going to be 3, 7, 2, and we're going to have 8 additional spaces. Now, the 1, 2 means I've already moved it 2 times, and then I'm going to have to do 6 more. So 3, 7, 2, and 6 more. 1, 2, 3, 4, 5, 6, and I'm all good. Okay. Now, in this particular case, it's the other way around. I'm going to have to move the decimal this way. I'm going to have to move it that way. So 1 that way, and then 10 more. Okay, so I go 0.123, 4, 5, 6, 7, 8, 9, 10, 1, 9, and then a 4. And I can just double check and go 3, 6, 9, 10, 11 would bring my decimal place to after the 1 and between the 1 and the 9. And so that's correct. I can do a double check on the last one as well. Go 2, 3, 4, 5, 6, 7, 8. And I have 8 decimal places just to confirm. All right, so that's scientific notation. We did a little bit of work on that. And then we went to finding the distance between 2 points, which was the last sort of unit on in this particular last lesson in this unit. Okay, so the first thing I want to do is, in this particular case, is I can plot my points. So A is 2, X is 2, 1, 2, down 1. And there's an assumption that you know how to plot and understand the Cartesian plane, okay? But we did do a little bit of review on that. So I labeled that, and then I'm going to label the next point, which is 5, 1, 2, 3, 4, 5, and up 3, 1, 2, 3. And there we go. And what I'm really looking to do is draw this line here. That I want to find the distance between that line. And so typically what I do is I create a right triangle, and I count off. This is 4 and this is 3, and I use my Pythagorean's theorem to calculate that. So this is c squared equals a squared plus b squared. And so I have to, sorry, by the way, that was the capital B. And you notice these are small letters, these are big letters, they're not the same. So this happens to be A, this happens to be B, and that becomes c squared equals 3 squared plus 4 squared. C squared equals 25, and that means C equals 5 units. Okay, and that's basically the process there. You might want to label your X and Y just because, that's the nature of how the beast works, and whenever we're graphing anything is that we label X and Y. If arrows weren't on your lines, on your axes, you should do that as well. Nice, easy bonus marks or simple marks, or in some cases, small deductions, right? All right, let's move on to the last one. What if I don't give you a table to do it and you just have to do it on your own? Well, you can use this wonderful formula, which is x2 minus x1, y2 minus y1. Okay, so remember, this will be x1 and this will be y1. This will be x2. This will be y2. Essentially, what you're looking for is to substitute this in. So you might, the proper way to do this is to say d equals square root of x2 minus x1 squared plus the square root y2 minus y1 squared. And so you substitute your values in. So x2 is -8, and x1 is 4, so that's -4. That's going to be squared. We're going to draw our hat way over. Plus bracket y2, which is 12, minus 3, bracket squared. So d equals, in this particular case, I believe it works out to -8 minus 4 is -12 squared. So -12 squared plus -9 squared. And we're going to square root all of that. So d equals 144 plus 81. I'm going to square root that. I believe this works out to square root of 225. I got to double check that, just make sure. 144 plus 81. Yes, that is correct. And that works out to 15 units. And that's your answer at that point. Okay, again, it's not really a word problem, so you don't have to write a therefore statement. So that's it. All right, and that was the entire unit of exponents that we used exponents. We basically covered topics like distance between 2 points, scientific notation, Pythagoreans, and square root, and then of course the exponent laws. And that sums it up. Hope you enjoyed the lesson, and go do the worksheets, get practiced up for your common activity. We'll see you next time.